Another type of problem that can be complicated if you don't have some way to help with it, but with a table can become really quite simple, is with mixtures. And mixture problems can apply either to liquid mixtures or to solid mixtures. Solid mixture would be like, a typical example they use in the book would be mixing two different types of hard candy. Where you weigh it by the pound and you would mix it together and you get a mixture. So that's what a solid mixture would be, that type of thing. Another place is if you do yard work, if you went and bought a different combination of topsoil of different grade, you could mix that. We're going to look at the liquid mixtures. I think that's maybe a little more applicable to what you're doing or what you might do or might need this for. And one example I can think of, maybe not so much anymore, but it used to be if you had kids and you needed to give them some medicine, you might have to dilute the medicine because it was too strong. So how much would you dilute it to get a certain value? Usually it would tell you. This way, we're going to look at how to predict the amount for specific concentrations. So we're going to look at liquid mixtures. When you're working with liquid mixtures, the concentration of the mixture is a percent number, which is what percentage of that total volume of liquid is the pure substance. The rest of it's water. So if you have an acid, say, 100% acid would be completely acid. A 10% acid solution would mean 10% of your volume is acid, 90% is water. So the percent number, when you're talking about liquid concentrations, is how much of the pure substance is present in this overall volume. If you have 100 gallons and it's 30% something, then 30 gallons of that 100 is the pure substance. The remaining 70 is water. Almost always water. Sometimes there are other things that dilute chemicals, but we're going to assume water for what we're doing. So the rate, and here it also talks about a rate, but it's a percentage. It's not a speed. It's a percent of concentration. And it's how much pure substance. When you mix two things together, you have something at this strength and something at this strength. If you mix them together, you get something at a strength in between, right? It's not as strong as this, it's not as weak as this. So your final concentration must always turn out to be in between the two you mix. Can't be any greater, can't be any less. It has to be in between. So that's going to always be true. Using a table for this is also very helpful. I know I struggled with this some when I was working these problems. Very simple with the table approach. And with mixtures, it actually tells you exactly what the equation is. You don't even have to guess. It tells you. So let's look at what we're working with. To make a table, you still need a formula. The formula when you're talking about mixtures, and I'm going to say it in words and then we'll put the symbols up. The concentration, that's that percent, times how much you have. So you've got a solution of something that's at some concentration. You have a volume of that, so many gallons. The concentration times that number of gallons is how much of the pure substance you have. So what we're going to do is we're going to make a table which uses concentration, volume, and I'm going to call it quantity. That's the quantity of the pure substance. Concentration times the total volume equals the volume of the substance. Concentration, volume, and quantity. So this column is how much of the pure substance do you have. This one is how many gallons or how many liters. This is your concentration, that percentages. When you're working with mixtures, you need 3 rows because you're always going to be mixing 2 things and winding up with a third. And you need to identify all 3 of them. So you're always going to have the 2 things that you're mixing together, and you're going to have what you wind up with, the mixture. So first solution, second solution, mixture. Again, first column is identifier. Call it anything you want, whatever will make it clear. Concentration is going to be a percentage. Volume will be gallons liquid, or gallons, liters, something of that sort. Cups, some way to measure volume. Quantity is going to be also volume. Everything's liquid, so the quantity of pure will also be in the same units of volume as the overall quantity. So if you say you had 10 gallons at 50% concentration, then that's 5 gallons of pure. Same units.
Remember, these 2 volumes must add up to give this volume, and these 2 volumes must add up to give this volume. This is an example of a mixture problem where we have liquid mixtures that we're going to combine to get a third mixture. In this case, we have 25% antifreeze, one solution of 25% antifreeze, and a second solution of 10% antifreeze. We have 5 liters volume of the 10%, and we want to wind up with a 15% solution. So if I add 25% concentration to 10% concentration, I'll get something in between. How much do I need to add in order to get a 15% solution? We're looking for how many liters of 25% solution to add. So let X be the number of liters of the 25% solution. I'm going to use the table again. My identifiers for this one are going to be 25% solution, 10% solution. Those are the 2 original ones I'm combining, and I want to wind up with a 15% solution. With that kind of terminology for my names, my concentrations are natural. My concentration is for 25% solution is 0.25, etc. The other pieces of information that I know that I have 5 liters of the 10% solution, and I know that I will have X liters of the 25% solution. I can put those 2 into the volume column here. I can put the X here, I can put the 5 liters here, and if you recall, in this column, this plus this must equal that. So when I put those quantities in, I get X and 5. Then when I add them, I get X plus 5 in the 15% solution. I filled 2 columns. I only have 1 column to go. That I get because the concentration times the volume equals the quantity. So I'm going to get 0.25 times X goes here. And so forth for the other 2 rows. That gives me this set of information filling out the table. So here's my table. I have one simple step left to do. In the mixture problem, because this column must add up and this column must also add up, which means that this plus this must equal this. Putting those together, I get my equation. Simple linear equation, solve it in the normal method, and I get x equals 2.5. X is a volume, therefore it must have volume units of measure. In this case, my units of measure for volume are liters, so the correct answer is x equals 2.5 liters. 2.5 liters of 25% solution must be added to 5 liters of 10% solution to get a 15% solution. By the way, it will turn out to give you 7.5 liters of that 15% solution. Second example, this person wants to mix 10% alcohol with pure alcohol and wind up with a 30% solution. If he has 7 liters of the 10% mixture, how much pure alcohol is he going to need to add? I don't see a concentration for pure alcohol. What do I use? Pure means 100%. So the concentration of the pure alcohol is 100%. Here's my table. Use the identifiers 10%, 100%, and 30%. How do you write the 100% as a fraction, or as a decimal fraction? It's just 0.0. So I can fill out my concentration. My volumes, I have 7 liters of the 10%. I want X liters of the 100%. So I wind up with X plus 7 liters of the 30%. Multiplying concentration times volume, I get quantity. So I have 0.7 for my quantity on my 10% solution, 1x in my 100%, and 0.3 times x plus 7 in my 30%. Adding up this last column, this plus this equals this. I get my equation. Solving the equation, I get x equals 2 liters. Thus, 2 liters of pure alcohol must be added to 7 liters of 10% solution in order to wind up with a 30% solution. And that will provide you with 9 liters of that 30% solution.
Everybody read question 34. Now you can work that without a table, but I suggest you might want to try it. What's your table going to look like? Or is anybody using a table, or is everybody just working it by trial and error? Okay, what's the table look like? Well, okay, if you're going to have a table, you need to know what it is you're putting in where, so you need some headings. What are the headings on our table going to be? Okay, there's an ID header. So there's an ID. What else is there? There's a concentration column. Volume. And what's that the volume of? Well, no, I mean, what type of volume is this? It's the mixture stuff, the dilute. It's not the pure. And then what other column? Quantity, and that's the quantity of the pure, which is also a volume quantity. Okay, now let's start putting things in. Before we put any numbers in, let's make sure we know what it is we're putting it into. So what's going to go in this ID column? Okay, so you want 30% here? Say it again. And you got those from what? Why 30%? And is this the what? Do they go in this order? Is this the right order? Well, there is a specific order you need to have. Actually, one of them needs to go in a very particular place, but the other two can be switched. This is the final, right? That's what you want to wind up with. It needs to be on the bottom. The other two you can switch. So these two doesn't matter, but make sure this one's the last one. Okay, and what do we have to work with? What do we put into the table? 18 liters of what? I'm sorry? The 18 goes here, not here, not here, but here. Top one. Okay, so you say 18 here. Okay, what else do we have? So I put 30% here. Right, decimal. Right, okay. What else do we have? So we're going to call the amount we put here to be X. Is that what you're saying? And then we're going to put that here. Okay. Why? If you add 2 gallons to 1 gallon, you wind up with 3 gallons, don't you? It has to be the sum of the quantities, the volumes you add up. Put these together, it has to give you the total amount you have. That's why it has to be X plus 18. There is no other choice. Okay? We still got a whole blank column there. What do we do with that blank column? Multiply what times what? Okay, nice full table. Is that the answer to our question? I don't see an answer yet. How do we get to our answer from here? Okay, you need an equation. Where's the equation come from? How? We just did a cross, and that didn't give us an equation. That just gave us the third column. Right. This column and this column, the sum of the first two must add up to give you the third one. We've already used that to get this here, so we can't use it again. There's no new information. But we have not yet added these and set them equal to that. That's what gives us our equation in this problem, is to add those two together. And set it equal to the one on the bottom. And that's a pretty simple equation to solve. So what's the solution? And what's the solution and what's the answer to the question? What's the solution to the equation? And then what's the answer to the question? They may or may not be the same thing. What's the solution to the equation? That's the solution to the equation, and then in this case, the solution is the answer to the question. once you put the units on it. So 7.2 liters is correct. This is not a magic trick. What this does is it's an organization. It organizes your information to help you figure out how to get these pieces. This is the equation that needs to be solved. And you can get there without the table. It's much harder to get to that equation without the table. Okay, mixture problems. Motion problem works the same way. With a motion problem, you remember using distance equals rate times time. In a motion, you're either adding, subtracting, or setting equal. And when you have two objects moving, remember the way to help identify whether you're adding or subtracting is, are they moving the same direction or are they moving opposite directions? If they're moving the same direction, you subtract. If they're moving opposite directions, you add. If it's equal, there should be something in there that says they're the same, same time, same distance, same rate, something equals something, that sort of thing. You could have words like 1 hour more than, or we had an example, 1 hour less. Those kind of things indicate adding or subtracting is going to be your equation. But your equations from motion is always either adding, subtracting, or setting equal. Right, this one is a little bit less friendly, perhaps. What you do, look at is number 23, motion problem. And pay attention to what the statements say. And there are key words here to help you identify equations. You get a table that looks something like that. Hopefully I got the table right. Did I get it wrong? How would you get an equation out of that? What other piece of information has not yet been used? 1.5 miles apart. We haven't used that. How do you use it? You're going to need to use it, so how? How do you use it? What does it apply to? It's a distance, so it applies to the distance column, doesn't it? Okay, remember I said on this type of table, you're either going to add, you're going to subtract, or you're going to set equal. Are these two things equal? No. They're different. So we're not going to set them equal. So we're going to add or subtract. Why are we subtracting? They're going the same direction. That was that other clue. Same direction you subtract, different directions you add. They're going the same direction. They're running the same race. They're not running it backwards, or one of them backwards. So they're going the same direction. So we're going to subtract. What are we going to subtract? Distance column. And we want the answer to be positive. So what order do we need to subtract in? The big one minus the small one, 7x minus 5x. And that gives us what? What's x equal to? What? I couldn't hear you. Looks right to me. But does that answer the question? What was the question? Does that answer? How long before they're a mile and a half apart? 0.75. What else do we need? .75 what? Days? This is some kind of time unit, isn't it? What units does this have on it the way we built this? What units does this have on it? This is speed, right? What units does it have? So those are miles and hours. What units did we use over here? So what does that make our time have to be? Hours. So this is 0.75 hours. If you choose, you could convert it to minutes. What would it be in minutes? 45 minutes. Both, either one's fine. In a homework problem or on an exam, you need to look at what the different answers given your choices are to make sure you choose the proper one. If it gave you 0.75 hours and 30 minutes, or maybe it gave you 45 minutes or 0.7 hours, you know, maybe if those were your only two choices, don't be misled by the fact that one of them is hours and the other one's minutes. Make sure that the size of it is the correct size, despite what the units are. The units might change as long as the magnitude is correct. Okay, so doing this type of problem. This class, one of the points of emphasis is to be able to solve applications. So we're going to be spending a little bit of time as we go through looking at things like this. How do you take the math and put it together with a situation in order to answer a question? And, you know, we're going to use fairly simple examples. You have to convert from the situation. In a textbook, you're going to be given a written description. If you were trying to do something for yourself at home, you're going to have to figure out what the different conditions are. If you're trying to decide how many rolls, some people may, how many rolls of wallpaper you need to wallpaper a room. When I was growing up, that was the main way we did the walls, was wallpapering. Back then it was a lot more difficult than it is now. It went over boards rather than over sheetrock. But now it's more of a decorative thing where paper is used for special decoration. But if you're trying to figure that out, you might have to do some calculation. A roll will cover this many square feet. Well, how many square feet do you have? Well, I don't know. So, you've got to come up with how does that fit together. And part of it is, doing a little math. You're going to have to put together some concepts and do some calculation to say, I need 5 rolls, or I need 6 rolls. Or I guess you could buy one roll, put it up, and so realize you're short, and go buy another roll and put it up, realize you're still short, and go buy another roll. Keep doing that till you get enough. Price of gas nowadays, you probably don't want to do that. So making the conversion from the situation into mathematics is part of what you need to do. The mathematics is a second part. Then using the result of the mathematics to answer the question. There are actually 3 pieces to it. Converting from situation to math, solving the math, converting from the math to the answer to the question. And we'll be looking at this as we go through.